Thank you, everyone. It's 9 o'clock and we'll begin our session now. I'd like to introduce to our presenter today, Dr. Thang Tran, our principal engineer at Andes. Thang?
Okay, hello everyone. So, okay, let's start. I'm Thang Tran, and this is the third part of the 4-part series where we go into details of each of the factor instruction in the RISC-V factor extension ISA. Okay. Okay. And so the agenda today is basically all about the factor instruction. So there's a memory, compute, and permute instructions. And so these are some of the terminology that I will be using. This is the same slide that will be show up on all the presentation. There's the integer reservoir, the vector, and then SEU is the element width, and then Elmo. This Elmo and VLEN are probably the two most important thing. It's about the vector raster length in bits, and then you had the Elmo is the grouping of the vector raster. And so this is the slide from last webinar to remind that when we have Elmo equal 1, we basically have 32 vector raster, and each one of these is 512 bit. When Elmo equal 2, we only have 16 vector raster and all even number, and the width of each vector raster is basically 1,000 bit. And so when Elmo equal to 4, we come down to 8 vector raster, and the width of the vector raster is 2,000 bit. And then when Elmo equal 8, now we only have 4 vector raster total, and the width now is 4K bits. Okay, and so if when Elmo equal 2, 4, or 8, and if any of the raster is not listed here, then it's basically they will be illegal instruction. Okay, let's start with the memory operation. So basically, load store operation are moving group of data between the vector raster and memory. So for Andy, we implement unaligned addressing, so there are no restriction on the alignment at all. There are 4 basic type of addressing. There are unit strike, basically consecutive element in contiguous memory, and non-unit or constant strike. They are in strike memory. Strike is the distance between 2 elements of a vector in memory. Index scatter is basically randomly offset in memory from a base raster. And then segment, it move into multiple contiguous field of memory to move into a consecutive number of vector raster. And this can be unit strike, constant strike, or index. We do not implement atomic load store for vector raster at this time. Okay, so alignment is very simple. If the data is unaligned, then you have to have 2 fetch in order to get, say for this example, to get 30 bytes of data, then you have 2 fetch. The first fetch is to basically get by 25th to 31, and then the second fetch is to get the rest to fill in the data. Okay, so it basically requires 2 low to get the data, or vice versa, to store the data into memory. The format, so the first set here is basically a low instruction, vector low, and the second set here is for the store, and then the width. So we do not want to be overlapped with the coding for the floating point low store. So we do not use the code here, the 3-bit here are not used. So we only use the other coding for the vector. And so there's an extension bit here, but it will be, for now, we all have 8, 16, 32, and 64. The other 4 is reserved when we have, we can go to 128 to 56 up to 1 kbit of the memory element width. Okay, and so the opcode here, basically we had the unit strike, the index unorder, the constant strike, and the index order. So the difference between the unorder and the order is that in the order, then you had to load element 0 before you can get to element 1, before you load element 2 and element 3. In unorder, you can actually load, in one cycle, you can load 0 and 5 and 10, and then the next cycle you can load 1. So the data that you load, it basically can be in any order. It's the same thing. This is for both the load and store instruction. And there's some special case that where you can have a unit strike for the whole register, or you can or different type of load store operation, and that including the load fault-only-First. Okay. So there another terminology that is the affected mode, and basically the affected mode is because the instruction can change the width, can change the width of the element. And so when when we define the type, you can define the element width is 16-bit, Elmo 1, and VLEN equal 512. Well, VLEN you cannot change, but the other thing you can change. So remember from last webinar, when you define the V type, and when you set the V type, and it means that for the element width of 16 and the vector length, rest of vector length is 512, you have 32 elements. So all vector instructions are operate on 32 elements, regardless of what. It will always operate on 32 elements. So when you had the vector load, that load 16. So basically the load 16 Elmo, so basically it will load into a single vector register. But if you change it to 32-bit, so now you load 32-bit, remember you still have to do 32 elements, but the element width is now 32-bit. So the effective Elmo will become 2. And now you have to load into V2 and V3. On the other hand, you can change it to E8. It means that, for 32 elements, it's now only fit into the first half of V1. So you only yield half. And so, or you have E64, then now the data is still loading 32 of the 64-bit data loading to V4, 5, 6, and 7. And so that will remain the same. And so in this case, it's an example here that you load the data into V1 and V2, and then you do the double width operation. So the W here is a double width operation. And so you can take and do V2 and V3, add to the side extension V1, and write the data into V4 and V5. And again, this effective Elmo will become 2, and the same thing with the store. The effective EMO will be 2. Okay, so let's talk about those special instructions first. So you have the load fault-only-First. It means that if the exception is for the first element, then take exception. But if the exception is not on the first element, then it's no exception. What we would do in this case is to set VL to the faulted element. And so, and the way that people would use this load fault-only-First is for the exit condition of the loop. So if you're going to load an unknown number of application element, if you're going to load an number, so you don't have any element that you want to load. So the example here, if you load if you want to fetch until the end of the TLB page, then you can just start fetching, and when it gets to the end of TLB page, it will create a for, and that's when you stop. And then you can set VL. So VL now consists, would tell you how many elements that you load into the vector raster. And so in the first webinar, I talked about strip mining, and this is basically the reverse of strip mining. Okay, so load store you can also do the load store for whole vector raster. And so in this case, the V type, the SDU is default to 8-bit, but you can use an F-bit to load into the multiple vector raster. This is a segment load, so you can load into multiple vector raster. And so no masking and all that. So else you have illegal instruction. And of course, if the V star is greater than the number of elements in the vector raster, then there should be a no operation. And the use case for the load store of the whole raster is for fill and spill. When you do a context switch, you just want to take all the vector raster and put into memory and then bring it back. Okay, so the example here for the for-only-first load, then in this case, you set element width to be 8-bit, and so basically 4K bit or 412 element of 8-bit. So you load in that, and so you can do the for-only-first load to a vector raster. And basically, if there's a 4, then it will be stop. And so you can also set the mask to basically to any byte that is 0. And you can get the number of bytes that it fetched by using this command to basically to read VL. So in this case, TA is enabled because TA is basically to use to write 0 to the element after the faulted element. So, and you can have that information, so you can set up the mask if you want to. Okay. The unit strike is basically to the continuous memory. So element 0 go to 0, 1 go to 1, and so it's pretty straightforward. Strike up 2. It means you skip every other element to put into the vector raster, or strike up 8, so every 8 element. And in this case that you can actually set the strike equals 0. Strike equals 0, it means you take 0 and put into all the element of the vector raster. Okay, so for the gather-scatter memory access, so you can have a base address, and the VS2 is defined to say which the offset, define the offset from the base address to load the data. And so if the offset is 2, you basically take 2 to put into the first element. Offset is 8, so you take 8 and put into here. And the store is the reverse operation. If the index is 15, then the first element will go to the address or the element 15 here. So it basically, it's just do, it's just using the VS2 to basically store the data into external memory. Okay, and so this is when I talk about earlier, when I talk about index and I mean, I talk about order and unordered vector memory. Say, for example, if this is 0 to 16 is one of your catch line, right? And so, and this, instead of 15 here, you have 31. right? And 31, it means it go to the second cache line. Okay, and if you want to do the order store, then you basically you have to do in order. It means that you basically you have to store into the second second cache line of memory, and then go back to the first cache line to do 1, 2, and 3, and so the store will be stored to second cache line, go back to first cache line, and go back and may jump to a different cache line to do the store. And so it's the order store you have to do at in order. But if you have unordered store, it means that if this one is 31, it doesn't matter. You basically you can store everything in the first cache line, and then go to the second cache line to do 31. That difference between order and unordered, of course. If you want to do it order, it would take a lot more time to do. So the indices are absolute, and they are not accumulative, and they can be in any order randomly. Okay, so the segment unit load store, it basically you load the consecutive data 0, 1, 2, 3 into 4 vector raster, and then go to the next one and load the data in 4, 5, 6, and so forth. And well, note that the fault-only-first is also allowed. And so if you look at the segment units strike, I mean, if you look at the segment low instruction here, it basically one instruction to load into 0, 1, 2, and 3. But if you have but you can do the same thing by having 4 instructions, right? So the first instruction would load into V0 with the stride of 4. So skip every 4 element to do the first one. So it can be accomplished by having 4 stride instruction to do the same thing with the segment low instruction, right? And so now we look at Elmo equal to 2, okay? So remember, Elmo equal to 2, you only have 16 vector rasters. So V0 and V2 are the valid vector raster. And so when you do the stride, it's supposed to go from 0 to 2, and then 0 to 2. So it basically 0, 1, 2, 3, 4. So the stride up 2, it means that you have to do that. A note here is that if you have a stride of 0, right, then what it means is that you're going to write 0 into V0 and V1, and you write 1 into V2 and V3. So it's the same data going to be written into all the elements when you have stride of 0. Okay, so segment index load store. And now, so if it says 7 here, then you put 7, 8, 9, 10 into V0, 1, 2, and 3. And then you go to 12, then basically 12, 13, 14, and 15. And notice that the data here can be overlapped, because you start at 8 here, then you can have 8, 9, 10, 11. So the data in the vector raster can be overlapped with each other. Okay, and so one example of using the segment load store is basically for matrix multiplication. And so say if you take the first matrix, multiply with the second matrix, you can basically put the data, use a segment load to put the data into here, right? And then the first one, you can use the index load to put the data. So now you can do the multiplication that of A0 to A3 to multiply with B0, B4, B8, and BC, and then continue to the next vector raster for the order 4 multiplication. And so you can use segment law for the purpose of matrix multiplication. This is just one example. Okay, so now we go to the compute formats, and so there the integer, and there's a floating point. And for the integer, you can have between the operation can be between vector and vector, vector and scalar, or vector and immediate. For the floating point, it's only between vector and vector, and or vector and scalar data. So the format, actually all the compute instruction had the same opcode, and then you had this field here to basically to say it's vector vector, or vector immediate, or vector scalar, all different type that you have here. And then for the operation, you would have OPI. It means that integer operation, or floating point operation, or the mask operation. And so there are 3 different types here. So like between vector and vector, you have integer, floating point, and multiply, for example. And the function 6 is basically to encode for all the all type of ALU operation. Okay. Right. So this is one of the standard of RISC-V, is that all the source operand, or the destination operand had to be in the same field in the instruction format. Okay, so let's talk about widening instruction. So you can have a double width. Okay, and so the W here mean that it will be double width. And so you can have a single operation go to double, or a double with a single go to double, and all that. So note here, the integer ALU, it basically you will need to do side or unside extend of all the source operand before you perform the operation. So the operation is actually double width operation. But for integer multiply and floating point, the operation is actually a single width operation, but the result is a double width result. So you return the double width. And as noted here, for double width, it means that you write then back to the vector raster. So you have to write back into 2 vector raster when you had a double width result. And basically, what we do with Ande vector parser is to break up the instruction into 2 micro-op, and actually the 2 micro-op perform independently. Okay, then you also have a special widening operation just for the single operand, that widening VS2 into VD. And so it can be a 0 or side extension. And so, but one thing to note is the SAW. So if you set up the SAW to be 32-bit, then your widening operation can only be 4, 2, or 4. So 8 will be illegal instruction unless you have an in4, the 4-bit integer. Then extension to 8 is legal. And actually, that's what we have, because we also support in4 data. But for the standard vector extension, that will be an illegal. Okay, so this is some how we implement the double width operation. For the double width operation, you basically take the right half of the data and then side extend it to from 16-bit to 32-bit and do the operation, and then write back into V2 here of all the double width operation. And then the second no-op, which is pipeline with the first micro-op to basically to do the left half of the data, to send it and perform and write back into V3. Well, now on the opposite, that you can have a narrow operation and from a double width. And so in this case, there are double width operation that the result will be single width. And this is a case of logical and arithmetic shift right operation. Yeah, let's get back to the same example that I had before to set the V type with Elmo 1 SAU6, the element with 16-bit and 32 element, right? And it's the same load to V1 and the same load to V2, okay? And then you can perform a double width operation followed by a double width to single width operation. And so now the data is written back to V2. And note that, when you have the effective Elmo equal 2 here, you had to write into 2 vector raster, or here you had to write into 2 vector raster. And the same thing that you also had to read from 2 vector raster also. Okay, and this is the example of the implementation, because one of the source operand is a full width, and so it still had to be 2 micro-op. Then you can start from the right half to be operated with V2, which is the double width data. And then when you had the result, it right back to the first half. And then the second half, it basically in the second micro-op to write back to the left half here. Okay, so now we're going to the detail of the compute instruction. So the integer arithmetic instruction, these are standard add, subtract, logical, shift, comparison, and all the min, max, multiply, divide. So they are standard instruction. And so I will only go through the instruction that is different than the normal scalar operation thing. And so, okay. So for vector arithmetic with carry instruction, okay, it is actually break up into 2 instructions. One is to produce the result, okay, and the other one is to produce the mask, okay. So the carry in is the same at the mask raster. So the carry in bit is in the vector raster 0, which is the same at the mask raster. So for the instruction, the mask had to be 0 because we cannot use the mask for the instruction, right? And so because this is actually the carry in that comes from V0 mask, so V2 plus V1 and plus the mask, okay? And then you do this, so you do this operation to write the result and do the same operation again to write into the mask. And so you need 2 instructions. And this is actually because the vector instruction or the RISC-V concept is to simplify the implementation. And so this is good because you only have a single vector destination raster for each one of the instruction, right? And a single write port per vector instruction. And this is, good for hardware implementation. That's why you have two instruction. But because you have 2 instruction that basically perform the same with the same data here, V2, V2, VS2, VS1, and V0, it means that the destination and the source cannot be overlapped. because if this is the same at VS1 or VS2, then you modify the data. Then when you come to the second instruction, you will get the wrong carryout, right? So it cannot be overlap. And it's also, this thing cannot be V0, of course, because if V0, then you also change the V0 mask. So that's the restriction. But for the second operation, the VM ADC, the destination result can be anything. So there are no restriction on the second operation. And it had to be in order, the VADC first before the VMDAC. And then the mask, there are two different types. I guess it's one is accumulate, which is basically VD is add to the multiplication. And the other one, the M-add, is that VS2 be added to this multiplication. And you had the same version for the sub, and the sub would accumulate. Okay. Then there's a merge instruction. The merge instruction is using the mask to select between the two operand. That two operand can be a factor, scalar, or immediate, to select between based on the mask. And so because we use the mask for the special purpose of selecting between the source operand, then the mask had to be set to 0. You cannot use the mask in this case. Because if the mask equal to 1, it's a move instruction. So this is same encoding with the vector merge instruction, but the special requirement is the mask had to be 1 and the VS2 had to be V0. The reason it's 0 is because we want to reserve the VS2 value, and we may have some other type of instruction that to be added later, but all the value for a VS2 are reserved. And of course, if VS1 VD is the same, then it's a no op. If it's a scalar or the scalar raster or the immediate, then basically you just splash that data into all elements. Okay. Then fixed point arithmetic. So now we have saturating, add, and subtract. And you also have average, add, and subtract. So this is basically pretty standard. Then you had a fractional multiply with routing and scaling and narrow clip instruction. So this is the narrow instruction that go from double width to a single width. Okay. So for fractional multiply and routing, it basically you would do a double width multiplication, shift right, route off, and saturate, and then clip the result. And you, in this case, you actually use the routing mode bit that in the CSR, and I talked about this in the last presentation. Then you had a scale, shift, and clip instruction, basically including the routing add, shift right, and then routing add and shift right, and then with the clip, then you shift and you just clip the data back to the VD, right? And it's basically it'd be a narrow, so from wide to narrow. From VS2 is double width, and the restore data is single width. Okay. Now for floating point arithmetic instruction, you have add, subtract, multiply, divide, square root, min max comparison, merge, integer. So this is similar to the integer. So these are pretty basic floating point operation. So I'm not going to spend any time on the floating point. Then there's a reduction instruction. So basically, reduction instruction, reduction sum. Basically, you take all the elements, you add them together. or you take all the element, you find what's the minimum of all the element, or what's the maximum of all the element. For floating point, you have two versions. One is the order, which you basically you had to add them in order, or unordered sum. It means you can add them in any order that you want, right? And so one example of the implementation is that we take the first half, we add to the second half, right? So you take the first half, you add to the second half, and you fold it in half every time. And so in this case that you have 16 elements, it would take 5 clock cycles to basically produce the result. And so for the integer operation, it's a single cycle operation. So you would take 5 cycles, so the latency of the factor sum reduction for integer will be 5 clock cycle. For floating point, each one of the floating point add is 3 cycles, so we take 15 clock cycle latency for the reduction of our floating point data. And for the order operation, it means that you have to do one at a time. So there are 16 serialized floating point add operation for 16 and 3 cycle edge. So the latency of the reduction sum for the order would be 48 clock cycle. Okay. So now you come to the mask, because you use the mask, so you have a bunch of instruction to basically to do to manipulate the mask. And remember, for each element you only have one single mask bit. So so one of the bit in the mask equivalent to an element. And that element can be 8-bit or 64-bit, but you still only have one mask bit for that. And the logical operation is, basics, AND, XNOR, OR, and all that. And so for some special case, that the logic, mass logical case, like if you can do the AND operation with this two same source. To basically, it's a copy operation. If the XOR with VD, it's basically the clear mask, or it's a set mask, or basically, so this is clear, this is set, one is XOR and one XNOR, or you can do invert the mask bit. So VL and V star is used with the normal operation, but remember, it's only for a single bit, not a vector, not the whole SEW thing, okay? And so of course, because everything is fit into, you only have one mask register, so there's no Elmo, so Elmo is ignored in this case. And then the rest of the mask instruction is basically, if you had a population count, so you basically, everywhere you have a 1, you accumulate and count them here. The VM first is to identify what is the first one that you see in the mask. Set before first mask, or set include the mask, or set only the mask, right? And then you have the V out instruction. Basically, it's the sum of all the preceding mask bit. So the first mask bit here would set the next element to be 1, and the second one will set the next element to 2, and the third one will set to 3. And then you had the index to basically put the index element into the destination register. Okay, the last one is the compute. I mean, is the permutation instruction. Okay, so the integer scalar move and floating point scalar move, so somehow it's in the permutation instruction. And this is at the move between element 0 and the scalar register, or it's at move between the element 0 and the floating point register. Okay, and then you had a slide, gather, compress, and the whole register move. And so this whole resemble is basically it's similar to the low star with the vector raster, the whole raster low star move. This is basically that copy one to the other, and you ignore V type and then Elmo and all that. It's just one raster at a time. Okay, so I'm going to spend some time on this slide, gather, and compress instruction. Okay, so there are two versions of slide. There's slide up by one, or slide up by by using the immediate data or using the data in the IS1 to basically to do the slide up, and then similar version with the slide down. Okay, so the slide up one is somewhat special because you basically slide everything up by one, but then you take the scalar or the floating point raster and put into position 0 when you slide up, right? And the purpose of this is basically you can do slide up by one and keep on shifting the data from the scalar raster. You can use that to test to make sure that the data in all the vector raster is correctly shipped into the vector raster. Okay, and the other type of slide, then whatever the value that you slide here. So in this case, you slide from 0 to 9, and so all the data just slide up by that. The bottom 10 element, if the STA is set, then it would be not that it means it can be anything. But if STA is not set, then basically it remains unchanged. So from whatever previous data is, it remains unchanged. Okay. For the slide down, you also has a slide down by one. It's similar to slide up by one, but now the most significant element, you get the data from the scalar or from the floating point raster, and then slide down by one. And slide down, it basically, again, you take the same value and you slide down. But the difference with the slide up is that all the upper element had to be filled in with 0. So all the upper element had to be had to write 0 into all the upper elements. So that's the difference between slide up and slide down. Okay, so the gather instruction, if you look at it, it pretty much basically very similar to the low star, the index low star. And so VS2 is the source, is the input, and VS1 specify the index, right? And so if the first element had the index of 5, it means that you need to get the data from the data element 5 from VS2 to put into the destination raster, right? And so the next one would be 7, then you had to put E7 in here. And so you look at from the VS1 here, the index here, and you look at the data element that you have in VD, all the E10 to E5, they basically the same at the VS1. So you had to randomly select it. And so with the gather instruction, you can actually using a vector unit load store instruction, because you can load the data in, and then you can use the gather instruction to shuffle the data around instead of using the index load store to load the data. In that way, you can use the unit stride load store and then shuffle the data as you want with the gather instruction. Okay, and compress. Compress is basically you have two vector VS1, And so if it's a 1, if it's 0, then you ignore the source data. If it's a 1, then you take the source operand element and you shift it into the first position of the destination. And the next one will take the next source element data and put into the next position, and so forth and so on. That's the compress instruction. So the compress instruction actually, it sounds pretty simple, but when you try to implement it, it's not that simple for implementation. But anyway, we managed to implement the V-compression instruction. So even for 512 element, so if you have Elmo equal 8, then you have like 500, and if Elmo equal 8 and the element width is 8-bit, then you have 512 element. And now you try to compress 512 element into the destination vector raster. And so for Andes, we managed to implement that in 13 clock cycle. And okay, and that's it. That's the whole presentation. Now I'm open up for question. Jonah, you
had one in the chat session. Advantages of RISC-V vector ISA to scalable SMID ones like ARM SVE.
Say it again one more time.
Okay, advantages of RISC-V vector ISA to scalable SIMD ones like ARM SVE.
So the ARM SVE is actually pretty much the same at the RISC-V vector processor. So they basically most of the instruction are basically pretty much the same. So I think in some case the code that we have is more optimized toward implementation in comparison to ARM, but the operation and the function are basically the same.
All right, a follow on how to expand vector extensions with instructions for custom SIMD hardware accelerators.
Okay, so yes, for Andes technology, we can add custom instruction, right? And so that's one of the thing about RISC-V is that allow you to add custom instruction. That's one advantage over ARM actually, because ARM it's very hard to add custom instruction. And so yes, we can add custom instruction. We do have requests from customer to add custom instruction. And so there are two types of custom instruction. One custom instruction, from our point of view, the one custom instruction that related to the load and store operation that basically outside of the vector processor. And in that case, we actually we do have the we do have so we did implement, and it was presented in the first presentation, that we have an actual port, we call it a streaming port, to load the data from the external memory to load and store data from the local external memory into the vector processor. That is actually a custom instruction. That's not in the standard RISC-V. And so that, we already have that. But now if you're talking about a compute type of instruction that you want to add, the way that we design the RISC-V processor, it's very simple to add a special, a custom vector instruction. We should need to know some really basic information regarding the latencies and the throughput and all that. Then we can actually add that custom instruction in. And our design is actually very simple, that that also allow us to add more functional unit. Say if you have an application, and in your application, there are many, say, floating point operation. We can actually pop in a second floating point option. I mean, the floating point functional unit into the side, so you can have, at how many or different type of floating point or functional unit that you want. You can have different integer of floating point functional unit. And right now, the current limitation is the total number of functional unit we have should stay with 16. And so right now we have 9 basically in our standard, but if you need more, you can actually add up to 16 functional unit.
Okay, I have another question. In the case of page fault for vector memory instructions, what happens in the scalar pipe? How the, okay.
I think I answered that one last time.
Okay.
That's what
I thought more was coming. Okay.
That's what the same question as last time. And so basically so when you have a okay, so one of the things that we do is for every vector load store operation, we only check the TLB once. With the first base address, we only check the TLB one. And so if there is a page 4 at that time, then the vector instruction is not even, in that case, it's not even started yet. And so you basically, you can take exception at that time and come back, and when you fix the page 4, then you can come back and start. And that basically from the integer pipeline, that's it, the same thing with from the CPU point of view. And so it would be the same for any CPU or any RISC-V, CPU load store instruction. If you have a page 4, you just stop and fix it and come back to the same point. So they're no different with the vector instruction at all, because the fall will happen before you start the vector load store instruction.
Okay, I think that's all the questions we have in queue. So if we have no other questions, we'll see you the next time, guys. Thank you for joining us today. And thank you, Thang, for a great presentation.
Okay, you're welcome. Okay, bye-bye.
Bye.